Okay, we're very happy to have Dean Robinson, who's coming from various UC schools. He's going to tell us about sterile neutrinos from heavy flavor anomalies.
Something like that. First, thanks for the invitation for coming up here again. Discussing I don't think I've been here for about 3 years or something like this, so it's very nice to be back. So what I'm indeed going to talk about are heavy flavor anomalies, in particular B2C town anomalies, I guess in the context of sterile neutrino explanations, but really I'm just going to use this as a pretext to talk at least first more generally about what these anomalies are and sort of take you on a tour of the sort of things you need to think about in order to develop new physics explanations, if you should in fact be doing that at all. I guess it might be helpful, just I guess not everyone here is a part of the physics, just to briefly recap the various experiments that will, whose information I'm going to be showing you in just a minute, or results. Just a reminder for B physics, there are two E plus E minus, or three, I guess, E plus E minus machines of relevance. One is Babar and Bell, which both ran, I guess, in the late 90s and early 2000s, and both produced about 1 billion BB bar pairs. There's Bell 2, which is just about to start taking data and will produce about 50 times as much luminosity. These are very clean machines. They produce B meters and pairs on the upsilon fluorescence resonance. And the other side of the coin is LXTV, which of course is a LHC. It's a proton collider, DP collider. It produces far more many BD bar pairs, or B plus X. And in particular, it can also produce not just the lowest flavored B mesons, but also strange or charmed or lambda beads as well in similar quantities. When you combine various efficiencies and reconstruction and difficulties with neutrals altogether, they end up having, in many different measurements, about the same statistical power between Bell 2 and LHTV. So, of course, LHTV has taken data, Bell 2 has not. So, what I'm going to talk about today, and I should maybe parenthetically also mention that in run 2, CMS took like 10 to the 10 BD bar pairs on tape with, I think, a Cellular Planning Tag, and we may be able to do something interesting in the space that we're going to discuss today. So what we are going to discuss today are beta charm processes, in particular the semi-tauonic decays. So in the standard model, these are interesting because these are just tree-level processes, just the beta charm and the semi-tauonic pair of our off-shell W. The branch formation for this is huge. If I combine all different modes with the lepton, either an electron, a muon, or a tau, it's around 25% of all beta decays. You have a huge statistical sample, and it's relatively theoretically clean because it's a true level process. What's more interesting, I guess, for us today is how this coupling here is allegedly universal. Whether I have a lepton that's a muon or an electron or a tau, I should have the same coupling here. And this means that up to effects of the different lepton masses, so the tau, of course, is much, much heavier than the other two, which will contribute to phase-space effects, or in some cases, hadronic matrix elements effects, because the tau, there's certain exposure coupled to the goldstone, which is proportional to the lepton mass. Overall, I should expect decay rates involving any of these three leptons to be the same up to basically this mass effect. So this becomes a fairly clean measure of lepton flavor universality. If I know how to map between this free quark process and the process that we actually observe, which involves bound states of quarks, mesons in this case, then I can also do things like measure VCB, the coupling up here. And this is a good opportunity to mention that the hadronic decays we're going to talk about today are going to involve either the beta D, which is a charm quark plus a light quark, or a D star, which is the spin 1 version of that guy. So if it turns out if you do try to measure VCB this way, you end up, depending on what approach you take, developing about a 3 sigma tension between various different methods. There's perhaps a discussion for another time is whether or not this has been resolved by certain technical changes in how you do this. I'm not going to discuss this today. But what you can do is factor VCB out of these decay rates by thinking about ratios of decay rates. In particular, the ratio between, say, a B to D or D star, so the bracket star means D or D star is appropriate. period to a tau nu versus the same branch versus the decay involving either an electron or a muon. These ratios are called RD and RD star. And as you can imagine, when you do this measurement, and Bell, Babar, and LXTV have all done this in various different ways, you end up with something slightly crazy happening. So what happens, and this has been going on, I guess, almost as long as the Higgs has been, since the Higgs discovery, 7 years or so, is you end up with signs of lepton flavor universality violation. So what you're looking at here is a plane of this RD ratio versus RD star. This red ellipse here is the current, and I use that word current with an asterisk next to it, which I'll explain in a minute, world average of the measurements from all 3 experiments, versus the standard model prediction, which is this tight little ellipse over here. And so taken together, I guess up to March 2019, you end up with about a 20 to 30% upward fluctuation in both modes, and a tension that's around about 4 sigma or so. You may notice that for the experiments that can measure both RD and RD star, there's a slight anti-correlation. The reason for this is because the D star decays predominantly to a D and a pi, and if you miss out the pion, then you reconstruct a D as a D star or a D star as a D, so you get an anti-correlated measurement. So there's a little update to this, which happened just at Morion a few weeks ago, which was a new measurement from Bell's semi-leptonic tag measurement. So in 2016 they did this measurement, and they could only do RD star then. They ended up with this green guy over here, and they just put out a new one, which is this green guy over here, which I guess the way to interpret this is to look at it combined with the blue guy, which is also a Bell measurement. So what this guy did is drop, so the full world average, so this is, I guess, a preliminary extra result that needs to be properly incorporated into the world average, including the correlations with existing measurements. But it nominally drops the result to around about a 3.x sigma result. So stay tuned on that. I guess this is doing what these type of anomalies tend to do, which is that the overall magnitude tends to drop while the significance stays around about the same. And maybe in a few years you may end up with it on top of the standard model, but at least at the moment it has not done that. But there's also a couple of other measurements on the way in this landscape. So the first one, so far I've been talking about exclusive processes, which involve looking for a particular final state hadron in the decay. But you can instead perform a search where you essentially look for B to charm plus any number of hadrons and a lepton and neutrino pair. It's an inclusive measurement. So this XE is something with an arbitrary variance. The reason why this is an interesting thing to do is because in the limit that the big quark mass is infinite, this inclusive process is just represented by the 3 quark diagram. And then you can correct this via an operator product expansion in the usual way, insert a complete set of states, and you can represent that as a time ordered product of currents in the 2-point function. So this is a theoretically independent calculation of a standard model prediction, and at the moment it's calculated to second order in this expansion, including 2 loop QCD corrections, and it's not quite precisely as the exclusive measurement. There is one direct and very preliminary measurement from Bell, which is this guy here. This is a thesis result. It is public, and I've given you the link, but it is not published. And the reason for this, if you read the conclusions of this thesis, is some concerns about mismodeling in the high lepton energy region, which can sort of affect the overall normalization of the result. But in any case, if you took this at half face value, this one would be fluctuating up to around about, I guess, 3 and a bit sigma tension itself. So that's one thing to look out for as along the way. There is another result that has been out for a little while involving the J psi. So here I replaced the light quark that was present in the B to D tau nu process with another charm quark. So I now have B to C tau nu with a charm spectator. The corresponding ratio Rj psi is measured at LXTV because they produce some small but not insignificant amount of B sub Cs. And this guy fluctuates at about the 1.5 sigma above standard model predictions. The standard model predictions here aren't under good theoretical control, I would say, so there's probably a limited amount you can say more about that. You can go there for a discussion of this. Those of you who are eagle-eyed may have noticed that in the plot that I showed you to start, that LXTV has not yet measured RD. And this is because, unlike the D star, where you can use that extra pion as a handle for projecting backgrounds, you cannot do that for the D. This measurement is been promised for a while and highly anticipated. So that would be really the thing that would be extremely interesting to see, especially given the fact that really what's changed in this measurement is the value of RD between the two different ways that Bell has tagged its measurements. So you may also be wondering, well, I've been talking about B to C tau nu, what about the other upside plot? What about B to U tau nu? So in other words, R pi, or R rho. So R pi actually has been at least implicitly measured. You can tease it out of this paper by Bell in 2015, and the result is 1 plus or minus a half. Obviously the statistics are lower here because this process is suppressed by VUB over VCB squared, about a factor of 100 or so. But this is broadly consistent with the standard model prediction, which is reasonably well known. And then there are a couple of other things coming down the pipeline in this space of measurements. One involves lambda C. So instead of having mesons, I could think about having baryons, a lambda B to lambda C process. Turns out these are interesting because, at least in heavy quark effective theory, these are theoretically cleaner than the mesons. The reason for this is that if you think of a heavy hadron as a heavy quark dressed by light stuff, the spin of the light stuff in a baryon is spin 0 for the ground state baryon, and it's spin half for a meson. So the effective theory is simpler for the baryons than it is for the mesons. And then there are a bunch of other interesting modes involving, for example, the strange version of these charm mesons. In particular, something called the D sub S double star. So double star corresponds to various excited states of these charm mesons, and they happen to be quite narrow, and something that Bell may be even able to do if it runs on the upsilon 5s resonance. So a few things that I'm not going to talk about today, but I should also mention. So you may have also heard about anomalies involving RK and RK star. I think Wolfgang was here actually. Someone recently spoke about this. So here's the updated numbers for this from Marianne. This guy floated up a little bit. It's still around the same 2 sigma or so tension. These should be, I guess, broadly. This one should be 1 in the standard model. This one has some cuts, and there is a large amount of literature that tries to link these together. We're not going to discuss how those areas of literature work today, but we can afterwards. So what I wanted to do, apart from that sort of brief survey, was discuss how you construct new physics explanations for these anomalies, and in particular, whether it would be interesting to think about using sterile neutrinos for this, and then at the end we'll discuss interesting UV completion that you can build taking advantage of particular properties of electroweak completions. So when you're faced with this type of anomaly, I guess the natural thing you want to do if you're a theorist is to think about things in terms of effective field theory. So what we would like to do is write down, for example, all the dimension 6 operators involving a charm, a bead, a tau, and a neutrino. A couple of rules I should mention at this point. One is I'm not going to think about new physics in the light lepton modes. So we're talking about an upward fluctuation of a ratio. I could equally suppress the denominator as increase the numerator. The problem with messing with these guys is that these guys are the thing that drive the measurement of VCB, and it's quite tightly constrained by CPM unitarity, and you end up running into trouble pretty quickly if you try to mess with these too much. So we're going to think only about physics involving the tau operators. And the other thing that you obviously want to do is make sure that the whatever simplified models you write down, they should be electroweak consistent, right, in the ultraviolet. And this has an interesting implication. Because the neutrino in the standard model is part of a electroweak doublet, this means that all the simplified models you can write down at dimension 6 to the standard involve couplings to the standard model that have to also be whose mediators have to carry a non-trivial either electroweak or colored charge. So sort of schematically, you can think about on the leptonic side of this operator, I either have two lepton doublets, and in order to have a charge current interaction, I have to have electroweak charges flowing in and out. I have to have at least a triplet there. Or I can think about I have a doublet and a singlet, and then of course I have to have something that's electroweakly charged on the other side of this. So this leads to some quite tight bounds. And to give you an example, the simplest thing you could think about is, well, let's just add an extra V minus A interaction that just lifts up this semi-leptonic decay a little bit. So here's the simplified model that can do that. Imagine a W prime that's a triplet of SU2. So it's just a Q bar Q, L bar L, W prime. This guy will generate, when I integrate out the W prime, the corresponding operator I want, the charge current here with the C bar B, tau nu. But also along for the ride are neutral current interactions that will generate large contributions of PP to tau tau. And that kind of is bad because that's quite a striking signal for something like the LHC to C. So to give you an idea of this, essentially the bounds on this are strong enough that in order to have a big enough contribution to lift up this operator, you end up being forced into into a region where the perturbative description breaks down. I need to basically have a quite somewhat lightish Z prime and a very large width to escape constraints, and I end up being forced into sort of this region here where I sort of a very poor resonance. See these guys for discussion about. Something else really bad happens when I play this type of game, and that has to do with flavor. So in particular, for this operator here, in order for me to generate the CB tau nu structure, I needed to have a second generation doublet here, a third here, and a third here, and something there, right, for the neutrino. So we can call this, like, if you like, a 2-3-3 type flavor structure. But because these are doublets as well, I necessarily also will produce B to S nu decays when I introduce this operator, or beta K nu, right? And that's quite well measured to the extent that large contributions to that are usually lethal. The other thing that you can induce are B sub S, B S bar, S bar B oscillations through this Z prime, which also can be equally dangerous. And so to fix this type of problem, you need to start adding extra epicycles that sort of tune away these operators by adding extra stuff, and things rapidly go off the rails. So what we're going to talk about today, our sort of pretext for continuing this tour, is a different possibility. So in your detector, of course, what you're really looking at is a B to a Chang hadron, a tau, and some missing energy. Actually uses some missing energy here as well. We'll discuss it in a second. So basically the conceit is, well, what if we promote this tau neutrino to a tau neutrino plus some sterile bar, right? After all, it's just another type of missing energy. In that case, I now no longer need to have this electroweak doublet present in my fourth Fermi operator. So this does in fact lead to at least one simplified model with a simplified, a much simpler electroweak structure. In other words, it can be neutral. And naively, then we would probably expect that we end up with looser PP to tau tau bounds because of this, and also because we may be able to produce relaxed flavor bounds, because I may no longer need to have any doublets present at all. It will turn out that this is certainly true, and this is somewhat less true, but we'll get there to exactly why a little bit later. So the first question you might be asking is, well, how heavy can I make that, right? Now that it's a sterile neutrino. Well, in the process involving the light leptons, the missing invariant mass in this measurement is essentially just the mass of the neutrino, right? Which should be 0. But in the experimental measurement, there is some degree of smearing. So what you're looking at here is the reconstruction of the missing invariant mass as a histogram from Bell. As a stack with the light leptons are in orange and the tau contributions are in red. So around 0, you can see that you end up in here with a peak, but it's kind of smeared. You actually get some stuff that's smeared to negative invariant masses, some to positive, and so on. So, and that smearing is of order about 100 MeV or so. Up high, the process involving the tau actually involves at least 2 neutrinos, right? Because the tau itself decays in this measurement. And so the missing invariant mass here is no longer 0, but some whatever the invariant mass of this neutrino pair is. So you can end up with much larger contributions, and as you move to higher missing invariant masses, now the tau mode starts to become important. Of course, the data becomes more noisy. So at this point, it seems that the conclusion you can make is, well, given what we know about the resolution of the measurement and that we anticipate a lot more data here, it's probably safe to tolerate around 100 MeV or so sterile neutrino in this measurement without causing things to go off the rails. In particular, you don't want to create some sort of kink down in this region from some threshold. So that's not to say that you couldn't, in principle, have something heavier. It really just means that because of the way the measurement is done, you have to produce new simulated data with a heavier guy and follow it through the whole analysis framework, which is something we'll briefly touch on a little bit later. But for today, the rule will be around 100 MeV or so is probably fine. The other thing you may be asking is, well, what about the mixing? So we're going to assume it's a sterile Majorana neutrino. Then it's bound from mixing with the light tau neutrino, typically scale like the ratio of masses. And in the regime that we care about, which is down here, effectively there are no little bounds that are relevant from any sort of beam dump or collider experiment. So we don't have to necessarily worry about that a priori. We will have to worry about some other stuff in a minute or two. Okay, so with those sort of ground rules, what we want to think about then are these, at dimension 6, these 4 Fermi operators involving a tau and an n right. So a couple of observations. One is, first, that there's going to be no interference with the standard model in these operators. So I'm always going to have an additive effect, which is what I want, because both ratios fluctuated upwards. We're going to normalize everything against the standard model, so in other words, against the usual 2 G Fermi VCB that appears at the front, which is equivalent to inducing an effective scale of around 900 GeV. And then the Wilson coefficients here, we're going to label by the chirality of whatever Dirac matrix we insert here or here, so we can have a vector left, vector right, scalar left, scalar right, or one tensor type operator. So just to write them out explicitly, 4 of these occur at dimension 6, so here they are. Scalar left, a scalar right, a scalar left guy, and a single tensorial guy. And the one that we care about the most, or at least a priori, is going to be this one, which you may notice includes no doublets at all, right? Which is the sort of thing that we wanted from the beginning. And these will match, so here I'm writing in I, J, K for all possible flavor indices. These will match onto, in the low energy theory, things involving charms and bees and towels and n-rights. So these are 4 of them. The 5th one is the V minus A interaction, and that one only arises at dimension 8. And you insert an extra H tilde, H dagger. And so on those grounds, we're not going to really consider that one much further in this discussion. One other assumption we're going to make is that, for simplicity, is that the only operators present here have the flavor structure necessary to make these guys. So we're going to assume essentially some degree of alignment, that those operators are written on a mass basis. as I mentioned a little bit later, you can actually achieve that in a dynamical way, but for the moment we're just going to take that as a fiat statement, and we're only going to consider, as I just said, the dimension 6 simplified models for the moment. One extra technical statement, which I may as well just say anyway, is we're matching between the ultraviolet and low energy theory at lambda effective, right, between the Wilson coefficients of these two different sets of operators. In principle, the vector operators don't run, but the scalar and tensor operators do. So you have to include some thresholds from the UV down to the scale mu, which is, you can take as somewhere around the B or charm mass. Typically I take it as the square root of MB and charm, the geometric. Okay, so now with those four operators in mind, you can start to write down all the possible simplified models. So the first one is the one we are most interested in, which is W prime, that's neutral under electroweak and color, it's just carrying a hypercharge. So the corresponding simplified model for this is this guy, written in a kind of a weird notation with the CQ and CN, just for reasons that will be simple later. And the corresponding Wilson coefficient for this is just this CVR character. Then there are two leptoquarks, which couple this U1 and S1, which couple to leptons and quarks in some annoying way, and they come with two different Wilson coefficients. This guy, this U1, is a scalar left and a vector right when I integrate out the U1. And this S1 guy couples to CVR and a linear combination of this scalar right and CT. This 8 here is an approximate number. It's 4 in the ultraviolet, and then evolves to around about another factor of 2 with that running. And then there are two other scalars, this phi and R2 tilde, which similarly come with two scalar Wilson coefficients, or this other linear combination of scalar and tensor interaction. So that's our entire space of simplified models that we can write down. Now, at this point, since I know all these guys, it's a relatively straightforward calculation, if you know what you're doing, to calculate what the values for RD or RD star should be as I change the values of these guys. And so I could represent this on our original space, this RD star plane, and just plot the full allowed regions for each simplified model. Where I have one Wilson coefficient, I can just have a contour in this space, so that's the case of W prime and R2 tilde, and for the other three simplified models, I can span some region. Phi spans the entire thing, that can be additive, U1 and S1 with a more constraint. Here the ellipses are the world average experimental results before the Morion so it should float down just a little bit. So the game that people tend to play when they do these types of analyses is the following. Well, given the right bit of computational technology, I can calculate for any value of Wilson coefficient where I lie on this plane for any simplified model. So what I can do is try to play a game where I try to get for some simplified model as close as I can to the best fit region, right? So basically, I'm constructing a 2-degree freedom chi-square in this space and projecting it, or inverse projecting it, back onto the space of Wilson coefficients that could get me within 2 sigma of this region. So like for the S1, I would want to sit in this space, and then I ask myself what values of Wilson coefficients does it correspond to sit in that wedge. Turns out, fortunately, that the best fit for all these different models involves Wilson coefficients that are order 1. So that, at least a priori, is okay. So before I show you what the results are of doing that type of procedure, and then explain why that procedure is actually a really bad idea, there's one little interlude that's kind of important. The interlude is that whenever I introduce a beta c tau n decay, I also necessarily introduce a BC to tau n decay. In other words, the B sub C to tau n decay is also introduced. It's fairly straightforward to calculate what the partial width of this process is in terms of Wilson coefficients. Everyone here could probably do it with a gun held to their head and sufficient motivation, right? The important thing, so I'm writing this here for the right-handed sterile neutrino contributions. If I included the guys with the left-handed things, it would modify this one with some interfering contribution. So the important thing here is that you all probably know that this decay is chirally suppressed when I have a vectorial exchange, right? I have to insert some sort of mass flip here in order to compensate for the quantum numbers of the B sub C state versus the outgoing fermions. When I have a scalar operator, however, it does that chiral flip for you. So you end up with a relative enhancement for scalar operators that scales like mb over m tau. And this means that I get a huge enhancement for if a scalar Wilson coefficient is present in the decay of the B sub C to tau nu, around about a factor of 3, which if I square it is a factor of 10. Right? The reason why this is bad is because, well, if you open up the PDG, you'll see that B sub C to tau nu is not a measured branching ratio. Right? It's quite a somewhat difficult measurement. In the standard model, it's around a 2% branching ratio. There's just not enough statistics to get down to that. But what is measured fairly well is the B sub C lifetime. And there are ways of estimating what the hadronic branching ratio should be in a semi-reliable way. So there are some branching ratios that are measured. Actually, their branching ratio is times the probability of producing a B sub C, but that's a different question. So in other words, what we have available to us is we know the branching ratio in the standard model because we know the partial width. It's easy to calculate. We know the lifetime. And we have an estimate for what the hadronic contribution should be. If you take those together, then it sets a requirement that the branching ratio of B sub C to tau nu probably shouldn't be bigger than around 10 to 30%, or you'll start to enter into a problem. That means that whatever is in here probably shouldn't be bigger than around a factor of the square root of 5, right, or whatever the corresponding thing is. I'm going to run it because I'm starting with 2%, right? I'm going to start to run into trouble. This, in practice, means that whenever I introduce a scalar current, I usually get nuked by introducing too large a B sub C to tau nu branching fraction. So now I'm going to show you what these fit results look like for these different simplified models, including this constraint of not making too much B sub C at the tau nu. So here is the W prime, is R2 tilde simplified model. So this is a space of essentially the chi-square that I was talking about before. How close am I to the central experimental value as a function of Wilson coefficient? And the blue dots are the 1 sigma region and the green are 2. And in orange or light orange, I'm showing the constraints if I require B sub C to be less than 10% or less than 5% respectively, just for a sense of scaling. So for W prime, that constraint is totally irrelevant. It's completely fine. For R2 tilde, the best fit regions here and here, or there and there, are inside this region where I'm starting to produce too much B sub C. So I have some sort of tension here that I need to start to be careful about. For the other three, I need to plot things on a plane because I have two different Wilson coefficients that I can turn on. So here are the other three, the U1, the S1, and the phi. Again, the blue is 1 sigma and the green is 2. Hopefully the colors are visible to you, this projector. So here, again, the white space is the stuff that's not going to run into a problem with B sub C. So there's some fit regions for this guy and this guy that are perfectly fine. For phi, however, which is a simplified model involving only scalar currents, I'm in deep doo-doo. It seems like that guy is kind of excluded, and R2 tilde is kind of in tension. This was all assuming real Wilson coefficients. You can do the same analysis with complex ones, and you end up with basically the same conclusion if you allow physical relative phases between Wilson coefficients. So at this point, looking at our space simplified models, the phi is kind of dead on these grounds, and the R2 tilde is sort of in trouble. But here is, I guess, our second interlude, which is did what I just do make any sense whatsoever, right? And the answer is sort of. And here's why. So it turns out, well, not turns out, it's a statement of reality. The way that experiments do RD and RD star measurements is not a counting experiment. They're fitting differential information on these decays along with complicated backgrounds and floating them together in order to extract an overall normalization for their signal mode. And this, so they're essentially doing a simultaneous background and signal Monte Carlo template float. And this means that the result you get for RD and RD star depends on the template that you use for your signal. So, to give you a sense of this, suppose, for example, for Babar's result, instead of using Monte Carlo produced with the standard model template, they produce Monte Carlo with a 2 Higgs doublet type 2 template with tan beta over n Higgs of half a GeV, inverse GeV. If they had done that, then the result they would have gotten for their ellipse on the RD star plane is not the green thing, but it would have instead been the orange thing over here. You get this somewhat massive template dependence. So this is, of course, a model where I've introduced a scalar, extra additional scalar current. So I guess the point is that if I was to do a self-consistent extraction, where I would have expected that I needed constructive interference, or constructive or an additive contribution to explain this anomaly, instead I would actually be in a regime where I needed destructive interference instead. So in other words, we need to get a sense of how important this is for the exclusions we just did, we need to gain a sense of how much differential distributions change as I change to different modules. And so to make this assessment, we used a software tool that we are developing in conjunction with Bell 2 and LXTV for their analysis frameworks, which is a Monte Carlo reweighter. And so we can So we can use this to look at what the expected variation of differential information looks like in these different best fit regions, to see if we could potentially are in a situation where we could anticipate a large fluctuation in the central values or the experimental data that we're attempting to fit the models to.
So my question is, I mean, it seems a little weird because nominally these R's are ratios of rates and they're inclusive. So it seems like what it really means, if there's this template dependence, is that they're not actually measuring the rate. So
they're not measuring the rate. They're measuring.
What are they measuring?
So what they're measuring is essentially, at the end of the day, they're pulling out a normalization. That's true. But what they're looking at is you imagine a space of, say, let's say 3 parameters. One is Q squared, it's the invariant mass flowing into the, or out of the BC system, right? PB minus PB squared. Another is the missing invariant mass, which I showed you in one of the histograms earlier, and let's say also the lepton energy, right? So let's take a 3-dimensional space. What they're then doing is they're applying some cuts to try to reduce the backgrounds in that 3-dimensional space as much as possible. But you cannot do so perfectly because you have all sorts of downfeed backgrounds from, say, the excited states, non-resonant stuff, and this type of stuff. So at the end of the day, what they do is they have to simulate a huge amount of Monte Carlo for their signal, include with these simulations for the backgrounds, and then float it all together against whatever they measured in this space. So they're really using the shape information to get in simultaneous fits to get a sense of how big the signal is versus how big the background is. So if you change the shape, it's the same in astrophysics, right? You can end up with a template where you end up turning signal into background or background into signal, depending on what you assume the shape of the signal or background was. So it's basically exactly the same thing happening here.
So you couldn't define some better observable then? I mean, it just seems like...
Well, yeah, so that's actually exactly what this is for, right? It's to allow them to, instead of them providing a value for RD and RD star that's done in the standard model template, what we're giving them is a tool that allows them to forward fold their analysis. In other words, for any given model point that they're interested in, they can do the full fit and extract and see if they are in tension with themselves. Because essentially what this green ellipse tells you is not the confidence to accept new physics in this regime. It just tells you the tension with the standard model. It tells you the confidence which you can reject the standard model template, not accept a new physics one. So yes, they are aware of this, and the long-term program using tools like this will be to be able to they do their own in-house analysis at the end of the day, fit not in RD and RD star, but say in the space of Wilson coefficients themselves, in terms of confidence interval on some Wilson coefficient in this space. If these anomalies persist, which at this point will be at least a couple of years before you can solve them. So what we can do as sort of a proxy for that is look at how the differential distributions look in those 2 sigma weirdly shaped regions I showed you earlier. So the W prime, which is the V plus A interaction. So the gray region here is what the 2 sigma fit region would look like in this differential space. The gamma D some observable. I'm just showing you a representative sample of these for single observables at a time, just to get a sense of what's going on. So just sort of, again, we'll show you the lepton energy, for example, or the opening angle between the 2 of these states, or the energy of the D coming off the D star, something like that. So the dotted line, by contrast, is a standard model shape prediction. So the W prime looks very similar. This would lead you to conclude that changing the template to include a W prime is not going to really change the result too much. For S1 and U1, the standard model is at least inside the fit region somewhere. There is some degree of variation, so you might expect that what you actually fit here as the best fit region might change by 1 or 2 sigma at the end, but it's not really going to change the conclusions too much. For R2 tilde, however, which is a purely scalar tense interaction, you really have quite a difference between what the standard model shape looks like and the signal, which is again sort of the same as what I just showed you in a different way. So here you might really suspect, well, actually maybe I can't exclude R2 tilde by doing the type of fit I did, because if I switch to an R2 tilde template, I might end up with radically different values of RD and RD star that don't run into this B sub C problem.
These templates are probably totally different for these different experiments too, right?
Yes, so this is truth level, right, at the moment. So this is just a proxy for this statement. In reality, you have to indeed look at the reconstructed information, the template of the reconstructed observables. Yeah, exactly. So, for example, for LHCb, they can't measure Q squared well at all because they have poor kinematic control. Okay. In any case, so having rescued R2 tilde briefly, you can actually really send it back to the morgue. And the reason is something I sort of hinted at earlier, which is B sub S to mu. So because the scalar right and tensor operators involve doublets, they automatically require that along for the ride B to S mu contributions. The running for these is around about the same, and you can write down the ratio of differential rates for, say, the standard model versus some new physics. And what really absolutely needs you, so this is this ratio, so you get 1 plus some non-interfering contribution. This Z is just Q squared over M squared. This is a strange notation. These F's are some form factors, which is some order 1 nonsense. Here are the 2 Wilson coefficients. This factor of 10 to the 4th kills you. Right? This is because you have a tree versus loop effect and a bunch of other things involving some large Wilson coefficients in the gene suppressor loop and this sort of nonsense. So the current bound is fairly tight. It's around only a factor of 2 above the standard model prediction. So at that point, you really can't have these scalar right and tensor operators being very large at all before you just run into problems. So at that point, you can, unless you have some sort of tuning, kill contributions from these 2. And so at that point, in this space, you would get rid of this guy. This guy would now also be in trouble for the S1. U1 is still perfectly fine phi was dead from the B sub C, and W prime is still fine. The next thing to consider is neutrinos. So let me just run through this quickly because we sort of went a bit more slowly. It's part of my post-cold voice. Whenever I introduce a B sub C determinative operator, I also induce a two loops contribution to a neutrino Dirac mass. Bummer. So if I have a Majorana right-handed guy, then based on your simple seesaw, I would want this combination with whatever the right-handed neutrino mass is to be less than whatever the active neutrino mass is, or I run into trouble. When I have a vectorial interaction here, I end up needing three chiral flips in order to couple whatever's going on here to the W in there. And so I get some degree of suppression. But for scalars, I only need one, for example, here, in order to couple into left, left, left. And so at that point, I get this basically the same model that the scalar operators run into trouble. So here, just writing down expressions for these mass terms, just estimating them. So for the vectorial piece, I'm basically fine. The best fit regions, these C's are order 1, so that's totally fine. But here, I now have like 100 EV Dirac masses that are roughly being produced. So this better not be too light, or I'm going to run into trouble with active neutrino masses. Coming from the other direction, the same operators also induce sterile neutrino decay. And here, unlike in the usual situation, it's this photon neutrino thing that dominates because the mixing here is suppressed versus whatever this operator that needs to be kind of large, like this RD star enhancement. So you have the same argument that I need that these scalar operators lift the otherwise required mass insertions, or would otherwise suppress these operators, and they end up with lifetimes that are a little bit too short. So for the W prime, if this is heavier than a keV or so, I'm still in a region where this is long-lived enough to be some dark matter subcomponent. I need to be careful about gamma ray bounds in the regime where this in this 10 to the 26 and 28 second lifetime regime, and I need to be careful about overabundance. But I could probably deal with that by adding some extra epicycle that decays late and dilutes this usual gain. If I'm light, then I'm very long-lived, but I do need to be careful about possible contributions to delta M effective. It turns out the estimate is the freeze-out temperature for this model is around about, this simplified model is around 10 to the, around a GV or so. And so you end up with contributions that you might be able to see, not yet, but possibly soon, with future measurements. And for these other guys, keeping in mind that the best fit regime for these is around about 0.2 and 0.4, with these lifetimes, unless I'm heavier than about 20 MeV or so, so I'm short-lived, I could end up with like CMB distortions and this type of stuff. So sort of the upshot at the end of this was that I need to be kind of close to this 100 MeV number that was sort of my naive upper limit. I will skip this advertisement for Codex B, just in the interest of time. It was just a statement that you typically end up with long-lived guys in these completions of these models, and you can look for it in certain places, like by putting detectors far away from stuff. In any case, the summary at this point for the effective field theory is these guys better have somewhat heavy MN, that U1 and S1. The W prime is kind of fine still. This particular operator is in trouble. These two guys are dead. So the next thing to think about is, well, these U1s are colored. So I can singly or pair produce them at the LHC. And then they're going to decay to some like crazy lepton quark or lepton-lepton final state. And actually, if I look at these carefully, I can end up from this like alpha LQ squared with itself, or alpha LD squared with itself, or this ZU squared or ZD squared contribution, actually produce these PP to tau tau contributions that I wanted to avoid in the first place. The next thing to do is to look at the constraints. So here is the U1. So the best fit, I'm just going to do this for the best fit point, just for the sake of simplicity. So the best fit point was actually these two values here. You can re-express this in terms of a relationship between a product of two of the couplings and the mass of the U1, and a ratio between the other pair of couplings. And then you have one free ratio left, which then fixes the ratio between the branching ratios of this U1 to either a top neutrino, a B tau, or a charm neutrino right. And so applying all the relative constraints here in this space of, so I have two things I can dial. One is MU1, and the other is this RU1 at this point. And so in this space, what I end up with is, well, the PP, the tau tau stuff's down here. I also get pretty strong constraints from U1 to B tau, but I can live in this regime and still have perturbative couplings. That's actually kind of fine. So this lepton model seems to be all right at the end of the day. S1, if I take the best fit point again and assume that this stable right got fixed by some tuning that would otherwise get nuked by B to S nu, I can play exactly the same game. I can write things in terms of the mass and a ratio of couplings that fixes all the branching ratios. And this time things are a little bit more dire. I end up with fairly strong constraints. I can really only live in this regime where I have this starting to become implausible ratio between these different couplings in the simplified model. 10, 100, or something like this. The Z or ZQ are both half, and this guy is ZD would be 20 or something. So that's a big person. Okay, so the W prime version of this I wanted to show as a UV completion, and I guess I'll try to end this on time. I'll just take you quickly through this last piece. So, what we wanted to do here was leverage the fact that everything in this W prime model involved right-handed fields only, and the mediator was not charged under SU3 or SU2 electroweak. So you could think about a 3-2-2-1 W prime model, where essentially you add in a right-handed sterile neutrino and you add in vector-like fermions and one extra order parameter. And think about a breaking that goes through two stages. One that breaks this SU2, SU2, U1 to SU2, U1, and then down to electromagnetism here. The game that you sort of want to play is, well, the contributions to B to C tau nu is going to be governed by the VEV here, but the bounds are going to be governed by the W prime mass. So I kind of want W prime largish, but I want this small enough to make this significant. And the other thing I need to be careful about is in this particular UV completion, I do have a Z prime floating around, a neutral current that can cause me trouble with this tau business. So the basic rationale here is that in this model you have couplings between the standard model like right-handed fermions and these vector-like left-handed guys. If we assume that everything again is in a line configuration, so I just have the B, C, tau, and N operators, and let's just skip that discussion, it's not really important. Then what I want to achieve is a large mixing between the heavy guys and the light right-handed guys. And so for the B, C, and tau, essentially the right-handed mass basis fermions could be written as just some mixing between the standard model-like guy and the vector-like guy. And I want to sit in a regime where this mixing is mostly with this guy, so I couple to the W prime. That's the basic game. So it corresponds to being in the regime that this is true. For the neutrino, I have 3 vial states and 2 Dirac masses, and so I have one combination that remains massless. And again, I want this guy to be the large piece because I want to couple to the W prime. And so I sit in the same area of VEV versus vector-like mass. And if I do this, then the W prime couplings that I naively had with these heavy vector-like guys now rotate and produce large couplings to my charm and B and right-handed tau and right-handed neutrino, where these C's are essentially these products of these signs, and they're one in these regimes. Of course, the problem with doing this is that I also get a large Z prime tau tau back when I do that. On the left-handed side, the mixing of the between the heavy and light guys is controlled by the Higgs VEV, and in the regime where the right-handed guys are largely mixed, then the left-handed mixing is suppressed by the ratio of masses, so it's kind of small. So that's good. And I need a massive neutrino, so I add a Majorana mass for this V prime. And at that point, then the mass basis NR guy scales like this Majorana mass times some suppression by the mixing. And I also need to be careful about left-handed mixings not messing up couplings to the Z. For example, I don't want the Z to be B to be distorted, because it's actually mostly, because it can contain a component of this left-handed vector-like state. So this places a bound on this mass ratio of this MQ. The mass of this vector-like guy should be 100 GeV or more, which is, I think, reasonable. And the other thing you could be worried about is messing up the ratio of Higgs couplings to masses, for example, for the B. Again, this thing you can convince yourself by just a simple exercise for the listener, is that this ratio scales like the cosine of this left-handed guy, and that in that regime is approximately 1. So if I take that all together, I can now produce for this UV theory what the collider bounds look like. And just as a reminder, here the Wilson coefficient and its effective scale is related to this coupling by these C's, which are now 1 in this particular area, in this regime of mixing, and the MW prime squared. So in other words, I can rewrite these in terms of MW prime in this combination. And I can then plot as a function of the branching ratio what the constraints look like as a function of the W prime mass. So in the regime where this C23 and CN3 guy, the mixings of the quarks and leptons is both 1, then the ratio of branching ratios between the tau nu and jets is 1 to 3, just by construction. So that corresponds to sitting right here. And at that point, it turns out that the CMS data is actually much more constraining than the Atlas one. And this is sort of a little statistical fluke. What is more annoying is that this data became available only recently, and this one was the one we originally had. So this makes a difference of, for this, this 25% point being between 1.7 GeV and 2 and a bit. Turns out to be a problem. You can alleviate this a little bit by adding extra generations of vector-like guys to suppress this branching ratio. And so that's what we do. And so if you just look at the Atlas data, including 2 vector-like fermions, what we can do is plot in the space of the VEV versus the coupling of this extra SU2, the region you need to sit in to explain RD star, versus the bounds, which the ratios are all controlled by these 2 parameters. So here, actually what is most lethal is W prime to tau nu. It's much more constraining than the Z prime to tau tau thing that we were initially concerned about. And so before October of 2018, it was still possible to sit in a semi-perturbative regime. Here, the contours are the Z prime and W prime masses on this space. With the new CMS data, what ended up happening is the same thing that happened to the original left-handed neutrino models. You ended up that the constraints became so strong that you can no longer really sit in a perturbative regime, and you need to instead think about being kind of light and very broad, and sort of squeezed up into this regime. So you need a broader W prime, which is I guess unfortunate. And this time, really what's doing it is not PP to tau tau, but PP to tau nu. the lethal thing here, which was a little bit of a surprise. Maybe it's obvious after the fact. So I guess just we can end things there. So what I hope I did was take you through a little tour of these beta C tau new anomalies in terms of what's coming down the pipeline and what has already come out the pipeline, and sort of how to think about ingredients for new physics explanations for these. And then in the case of this sterile neutrino thing, you do end up with having a W prime simplified model that's colorless, electroweak neutral, and flavor friendly, because I don't have to worry about the beta S new contributions. And it has a similar morphology and template to the V minus A standard model template, so I can be fairly confident about the types of fits I do with it. You can write down UV completions, but the collider bounds are more of a problem than you would naively think. And I guess I should also say that the leptoquark models are still viable in some perturbative regime. Is there anything interesting you can do in the ultraviolet for those, I guess, is a question to think about. So we finish there.
So why are the Atlas and CMS bounds so different?
It's just statistics, I think. It's just
There was a downward flip.
Yeah, Atlas is
events,
yeah.
events,
Atlas.
There's no.
Yeah, they just had a downward fluctuation. Not I don't mean in terms of the number of events they record necessarily, but just that the Atlas result fluctuated down by about a sigma, and the CMS one maybe fluctuated up by a sigma, and so one is just more constraining than the other in that tau nu mode. So, which is that's what you expect to happen when we have that's good thing that we have two experiments for this exact reason. Probably some version of this may still work, but it's because it is attractive from the point of view that you don't have to mess around with colored or electrolytic mediators. But that said, you also don't want to have to mess around with like a super broad, somewhat heavy state.
Just wondering if you've looked into less monogamma searches with it.
Into what, sir?
Let monogamma searches.
Let monogamma.
They might if they constrain some of these models.
So here, yeah, so the thing to keep in mind is that you need to, is that we sort of by construction thought about an aligned configuration where I'm only really turning on this BC tau nu operator or anything required by electroweak doublets. So for LEP, because it's a lepton collider, I would need to start thinking about electron couplings, which I sort of by fiat turned off. I agree that if you have like some sort of anarchic flavor structure for these operators, then that could become relevant. It's certainly true that you don't just get B sub S things that kill you, but also, for example, charm mixing starts to kill you, kaon stuff starts to kill you, and so it's equally plausible electronic monogamma could too. I agree.
Are there any other questions? If not, let's thank Dean again.